Electric generators produce virtually all of the world's electrical energy. A generator produces electrical energy from mechanical work, which is just the opposite of what a motor does. In a motor, an input electric current causes a coil to rotate, thereby doing mechanical work on any object attached to the shaft of the motor. In a generator, the shaft is rotated by some mechanical means, such as an engine or a turbine, and an EMF is induced in a coil. If the generator is connected to an external circuit, an electric current is the output of the generator. Here we start with the central component of a generator, a permanent magnet, which produces a magnetic field B between its poles. In its simplest form, an AC generator consists of a coil of wire that is rotated in a uniform magnetic field. Although not shown here, the coil of wire is usually wound around an iron core. As in an electric motor, the coil-core combination is called the armature. Each end of the wire forming the coil is connected to the external circuit by means of a metal ring that rotates with the coil. Each ring slides against a stationary carbon brush to which the external circuit, such as a lamp, is connected. To see how current is produced by the generator, consider the two vertical sides of the coil. Since each is moving in a magnetic field, the magnetic force exerted on the charges in the wire causes them to flow, thus creating a current. Considering the component of the velocity perpendicular to the magnetic field, right-hand rule number 1, i.e. the fingers of the right hand point along the field and the thumb along the velocity, and the palm pushes in the direction of the force on the positive charge, indicates that the direction of the current is from bottom to top in the left side of the length L, generating an EMF equal to BLV perpendicular for one side, where V perpendicular is equal to V sine theta, so that the EMF induced in the left side is BLV sine theta. Similarly, the current goes from top to bottom in the right side of length L, so that the total EMF for the loop, both sides, is 2BLV sine theta. Thus, current flows around the loop. The upper and lower horizontal segments of the loop of length W are also moving. However, these segments can be ignored because the magnetic force on the charges within them points towards the sides of the wire and not along the length. Finally, assuming that there are n loops of wire in the coil, the total EMF is equal to n times BLV sine theta. If we now convert from linear to angular variables, we have V equals R omega, where R equals W divided by 2, and theta equals omega t. The EMF is then equal to n times 2BL omega times W divided by 2 times sine omega t. Canceling the 2's and noting that L times W is equal to the area A of the loop, we have the EMF equal to NAB omega times sine omega t. Defining the amplitude of the EMF as E0 equals NAB omega, we write EMF equals E0 sine omega t. The relationship between the angular frequency and the frequency, f, is omega equals 2 pi f, where omega is measured in radians. This result is valid for any planar loop of area A, regardless of its planar shape. The peak, or maximum EMF, E0, occurs when sine omega t equals 1, and has the value E0 equals NAB omega. Since sine omega t changes sign, the EMF changes polarity as the coil rotates. This changing polarity is exactly the same as that discussed for an AC voltage. If the external circuit connected to the generator is a closed circuit, an alternating current results that changes direction at the same frequency f as the EMF changes polarity. Therefore, this electric generator is also called an alternating current, or AC, generator.